Okay, let's talk about net. So remind, Newton's second law for rotation says that the net torque on an object is equal to the rotational inertia times the angular acceleration. We can connect linear dynamics and rotational dynamics. We have force and torque, mass, and rotational inertia, also known as moment of inertia. And then acceleration and angular acceleration, and finally Newton's second law for both of them. And in these examples, Newton's second law is rearranged for both to solve for the acceleration and the angular acceleration. So we talked about this on Tuesday. We talked about the rotational inertia for a system of particles, which is the sum of their masses and the distances between the particles and the axis of rotation squared. This is for a system of particles specifically, but not an extended object. Extended objects have their own equations for their rotational inertia. And you can derive those equations with integrals. Obviously, we're not going to do that because this is not a calculus-based class. But I will just give you the equations. So not all of these are relevant to us. Oops. Okay. But I'll point out some of the ones that are. So we have a hoop rotating about its center. And its rotational inertia is mr squared. We'll skip this one. And then we have a solid cylinder rotating about the center. And that is 1/2 mr squared. So the length of it doesn't matter. We'll skip that one. And then a long thin rod rotated through an axis through its center. So that rotational inertia is 1/2 mass times the length of the rod squared. Long thin rod, another example for it is if it's rotated about an end instead of the middle, and that would be 1/3 ml squared. And then the other ones that could potentially be relevant for us are the solid sphere and a spherical shell or hollow sphere. So the solid sphere is 2/5 mr squared, and the spherical shell is 2/3 mr squared. Now let's do this example from Tuesday, but now we're not going to ignore the rod or like the mass of the rod. So let's do that. Okay. So let's write this out. Let's remember the rotational inertia for a rod about its center is 1/12 ml squared. Okay, so we're gonna have to refer to that one. And then for the situation, so for the rotational inertia of a system of particles, we sum up the rotational inertia of each particle. So similar idea here where we still sum up the rotational inertia from each mass source. So the rotational inertia, the total rotational inertia is the rotational inertia of mass 1. We'll call this mass 1, this one mass 2. Plus the rotational inertia of mass 2 plus the rotational inertia of the rod. So for particle, it's just mr squared. So let's do that. We have m/2, that's the mass. And then the distance is just r from the center. So that's just going to be m/2 r squared. And it's the same for mass 2. So m/2 r squared. And then 1/12 ml squared. So 1/12, and then it's a lowercase m because that's the mass. And L here is the radius, or is R, 2R, excuse me, is the length. 2r, and that is squared. So these first two terms combine to be mr squared, and then this last term, we end up with 2r squared, that's going to give us 4r squared. And 4 divided by 12, that's going to give us 1/3 mr squared. And then we can combine these two terms and we get 4/3 mr squared for the total rotational inertia. Okay, so this is again the same problem from Tuesday, but this time we're paying attention to the rod itself also. Let's look at another example. This time we have a solid cylindrical pulley. Its mass is 0.8 kilograms and its radius is 0.31 meters, and it's experiencing these two forces in the picture. And we want to figure out what the angular acceleration of the pulley is. So before we get too far into this, let's remember a couple of things. First, the net torque is the rotational inertia times the angular acceleration. So that's the way to get the angular acceleration. And then the rotational inertia for a cylinder, solid cylinder about center, is I think it's 1/2 mr squared. Okay, so those are just a couple of things we'll need to refer back to, but first let's just find the net torque. And that's where we use our torque table. So let's make it. So we have force, distance, angle, and whether or not it's clockwise or counterclockwise. So let's just draw our radial lines to connect so we can make sure, the angle is 90 degrees for both of our forces. And our first force we'll say is 12 newtons, the second force is 10 newtons, and then the distance is the same for both of them, it's just the radius, so 0.31 meters, 0.31 meters. And then the 12 Newton force would cause the pulley to spin counterclockwise, which is positive. The 10 Newton would cause it to spin clockwise, which is negative. Okay, cool. Now we can find the torque of each of these. We'll say this one's 12 newtons times 0.31 meters. I'll include the sine 90, but sine of 90 is just 1, so it goes away. So this gives us 3.72 Newton meters. This one is the positive one. And then torque 2, I'll put the negative sign here, 10 newtons and 0.31 meters. Also sine 90, which is also 1. And then negative 3.1 Newton meters is what we get for the torque of that one. And then our net torque, sum of torque, is going to be torque 1 plus torque 2. That is 3.72 Newton meters minus 3.1 Newton meters. That's going to give us a total torque or net torque of 0.61. I think I wrote it wrong before, so I'll have to double check my numbers. Newton meters. Okay, so that's our torque, but then we're trying to find the angular acceleration. So use that equation. The torque equals rotational inertia times the angular acceleration. And if we're solving for angular acceleration, that is the torque divided by the rotational inertia. Our torque is 0.61 Newton meters, and then the rotational inertia for the solid cylinder, not what it was, cylinder, there we go, 1/2 the mass, which is 0.8 kilograms, times the radius, 0.31 meters squared. And let's just, my number shouldn't be that different, but let's just make sure. 0.8 different for you on the square. Okay, it's a little different, but you can round it to be the same. So 15.9 radians per second or 16 radians per second for the angular acceleration. So for this one, we combined the things. We did the net torque, where we did our torque table, and then solved for the net torque. But then we also, using the rotational inertia for our object, we found the angular acceleration. So I think there's, yeah, one more example, and this one isn't, we're not going to use rotational inertia for this one. We just, this is kind of introducing you to the topic that Thursday is going to cover. But this is also an example from Tuesday, but this time we want to figure out what force would make the net torque 0 in this situation. So let's do our torque table still, F R theta, and I'll just say plus or minus. So 8 newtons, 25 centimeters or 0.25 meters. And we can look and see that both of these are 90 degrees between our radial line and our forces. So 90 degrees, 90 degrees. This one is the force we're trying to figure out, and it is 0.75 meters from the axis of rotation. And then let's see, let's try the trick with our writing utensil, and hopefully this is the right direction for you in seeing the screen. If it's not, do it on your own and use it that way. Actually, I feel like for you guys, I might be doing this wrong. So the 8 Newton force, that's going to cause clockwise rotation, so that's negative. And then the force we're trying to figure out is what is the opposite direction, so it would be positive. Okay, so our net torque equals 0. That's what we're looking for, 0 Newton meters. And it's also both torques combined. So see, we have our 8 newtons times 0.25 meters sine 90. Oh, that one's negative. Plus whatever our force is, 0.75 meters sine 90. So again, both of these sine 90s are just 1, so we can ignore those. And then let's first solve out what this is, and then we'll move it to the other side. So we have 0 equals -2 plus 0.75 times whatever our force is. And then we're just going to add that 2 to both sides. And we have 2 equals 0.75 times the force. And then we divide both sides by the 0.75. And we get 2.67 newtons as the force needed to make the net torque 0. Okay, so yeah, that one is just to give you a taste of solving for things when the net torque is 0, just like how we solve for things when the net force is 0. And that's all we have for this one. Yeah, see you later.